Hello and welcome back to another applied calculus lesson. Last lesson, section 5.2, we discussed and introduced what a definite integral was, and we discussed what it represented, that is the area under the curve. In order to move forward with this conversation, in this section what we're going to do is we're going to sort of do a deep dive into this idea of area under the curve and see what sort of subtleties actually lie in the depths of this conversation. So to begin with here, we're going to recall last lesson when we introduced this definition that when a function f is positive, if you recall section 5.1 and 5.2, we've only ever been dealing with positive functions. All the pictures we keep drawing, everything is positive. When f was positive, we said that this definite integral from a to b of our function f ended up representing the area under the graph of f between a and b. Specifically, we kept drawing pictures that looked conspicuously like this. Here's an a, here's a b, and there's our function f of x. And then we were sort of drawing a left and a rightmost boundary, and then we were attempting to try to figure out what the area is underneath the curve right here. This is essentially what we've been doing for a while. And we said here that the area was exactly equal to this definite integral from a to b. However, there's no real reason why f needs to be positive. F can very well be negative. We've encountered functions where f is negative. For example, our profit function. Most of our profit functions tend to start out negative because in whatever real-life situation you're in, usually you had to take out some sort of a loan or something before you start building out your company, and so you're in debt. Your profit is negative. So we do have to know how to compute areas under the curve when f is negative. It turns out that when f is negative, the resulting integral still returns area, but the weird thing is that the area it now returns is negative. So for example, the picture we might encounter is a picture like this. Again, here's an A and here's a B. That's the part of the picture we care about. And maybe our function starts over here, but the point is between A and B, my function is negative. So here's still my left and my rightmost sort of boundary, and the area that now I'm interested in is exactly this area down here. This area between a and b of our function f of x is still, it's still a valid area, but now it's what we're going to call a signed area. This area is going to be a negative number. So the area is still going to be the integral from a to b of f of x dx, but this is going to be negative. Whereas when our function was positive, the area that we found up here turned out to be positive. So we start to witness that if our function is positive, our area is positive. If our function is negative, then our area is negative. So what happens if your function between a and b is both positive and negative at the same time? For example, what if we considered a function where this is a all the way to the left, this is b all the way to the right? Maybe our function starts off positive, but then at some point it switches to negative. Well, our left boundary, a, and our right boundary, b, are given here. It should be worth noting, by the way, that when we referencing back this negative example, when we say, quote unquote, area under the curve, what this really means, this is equal to, we should maybe write it, this is the same as saying the area between the graph and the x-axis. This note, which we're going to highlight over here, this note is actually somewhat important because it might seem confusing at the beginning. I'm going to keep using the phrase area under the curve, whereas in this negative example, there's not really an under. Somehow the under is actually an over. So the area under the curve needs to be interpreted as the area between the graph and the x-axis. And so what that means is that in this picture down here, where the function is both positive and negative for a period of time, the quote-unquote area under the curve is now, I'm going to highlight it again in blue, it's going to be, well, the positive contribution is going to be what you want it to be, the area under the curve. But the negative contribution is going to be down here. But this is where things start to get a little weird, because this area is positive because the function is positive. This area is negative because the function is negative. So what that means is that if I go ahead and compute the integral from a to b of my function f of x dx, in this case, this large area, which is positive, and this smaller area, which is negative, is going to start canceling each other out. So this integral from a to b is not just going to be this area plus this area. It's actually going to be this positive area minus this area. This is a very subtle situation that we find ourselves in, but it is very important that we understand it. So I'm going to give you an example to make this more clear. I'm going to call this area A1. So I'm going to call this A1. I'm going to call this area A2. So this is equal to A2. The overall area that we're interested in here is going to be, well, we'll call the second area negative A2 because we want it to be negative, right? So what that means is that the integral is going to be A1 plus negative A2. But the total area is actually going to be equal to A1 plus A2, where you have to note these two things are different. This integral is its positive area plus its negative area, whereas instead, if I just say total area, that's going to be everything is positive, literally A1 plus A2. These two things I just highlighted are not equal to each other. One is A1 minus A2, the other one is A1 plus A2. Total area is literally, if I were to look at this picture and I wanted to, buy enough paint to be able to paint these blue regions, that's what I need. The integral is signed area, not total area. I noted up here that the area under the curve here of f between a and b, this is total area and it's equal to an integral, but that's because f is positive. So the important caveat that we're starting to observe here, write this in red, is that the integral is representing total signed area. Whereas total area is unsigned. So this is unsigned, where signed means positive or negative. So it's a little bit of a subtlety, but we have to be careful about it. We're going to take a look at an example now to help illustrate what I mean here. Let's take a look at a function. The function here is y equals x squared minus 1. We can draw a picture of what this looks like. Y equals x squared minus 1 is the x squared function that's been shifted 1 unit down, so that might look something like this, where this is a 1 and say this is a 2. This is a negative 1, this is a negative 1. This is my function. What we're going to do is we're actually going to take this picture, we're going to move it. I'm going to move it over here to the right, and then we're going to copy this, and we are going to replicate this 3 times. Because we're about to do 3 different integrals here. There we go. The first integral says, consider this function, as we've drawn it here, and compute the integral from 1 to 2. So this is computing an area under the curve. The area it's computing is 1 to 2. So here, that's the area that it's actually computing. Once we get to chapter 6, we'll actually figure out how to algebraically compute this integral. But for now, take it as faith that this area, which I'm going to call A1, this is equal to A1, and that area is going to be equal to 4/3. Whereas, if I wanted to compute the area, the integral of the same function, but from -1 to 1, that is going to be this region down here. Same picture, but different shading. What you'll notice is that here, the function is negative. So what that means is this area is going to be negative. I'm going to call this area negative A2. So it turns out here, this is negative A2. You'll have to, again, just trust me on the following fact. It turns out that this area is equal to negative 4/3. So what that means is A2 is equal to 4/3. So what that means now is if instead I wanted to compute the same function, but now I want the integral from -1 to 2, that's going to be, well, -1 to 1 was this region underneath the x-axis, and 1 to 2 was this region we first encountered from 1 to 2. Notice that this is going to be this area underneath it, which was negative A2, and the area over here to the right, which is positive A1. This is going to be equal to A1 plus negative A2, which in this case is 4/3 minus 4/3, which is a 0. This is a weird answer because, again, the way we introduced this was that we said, oh, the integral, it's the area under the curve. How can the area under this function x squared minus 1 possibly be 0? And this is why it's important to remember that the integral is returning signed area. So in this case, it turned out that the positive area that we got to the right of 1 and the negative area we got between -1 and 1 turned out to literally cancel each other out, so that the overall integral we're considering here is literally evaluated to a 0. Whereas, it might be worth noting that if I wanted to compute total area, not the integral, but the total area, it would actually be 4/3 plus 4/3, which is going to be 8/3. That's just literally the amount of material you'd need in order to fill in the shaded regions here. It does not care about positive or negative. The integral is signed area, which allows negative area, which means it allows cancellation. Total area does not have negative area, and so it's literally just adding up all of the different areas. In order to codify what we're trying to say here, we can say the following. When the function f is positive for some x values, but negative for others, then between a and b, the integral from a to b of f is the sum of the areas between a and b above the x-axis, where, importantly, we count that positively, because we're above the x-axis, as well as the areas below the x-axis, but we count them negatively. This is just a fancy math way of saying that this integral is measuring total signed area. That's the key. It's signed area. So let's take a look at another example. Here we have the definite integral of this cubic function from 0 to 4, and we want to interpret it in terms of areas. In order to do so, we need to have a graph. For the purposes of this example, I'll illustrate what that graph is. It may be helpful while you're doing your homework to maybe use a graphing utility in order to understand what the graphs might look like. For the purposes of this section, our objective is not to learn how to graph a function. Our objective is to learn what these integrals mean and how to represent them. So if we did take a look at a graph of this, specifically from 0 to 4, it might look something like this. It has a hump above and then a little bit below. It's actually going to be very similar to the first graph that I drew. We're coming all the way out here to 4, and we're starting at 0. The hump goes up to about 5 and down to somewhere near -5. And the x-intercept is going to be 2.38, where this is the function f of x, defined to be x cubed minus 7x squared plus 11x. This definite integral is again returning signed area. So everything above the x-axis, so we're going to note that we're going to stop our rightmost boundary all the way to 4. So everything above the x-axis, like this region right here, this hump, is going to return a positive area. So we're going to give that a name. Maybe we'll call that a sub 1. Whereas everything below the x-axis, like over here, is going to return a negative area. And so we're going to name that negative a sub 2. So what we find here is that we can actually write this entire integral as the sum of two integrals. The one integral representing a1 and the second integral representing negative a2. So if we were to write those out, we would note that a1 is representing the integral of the same function, which is x cubed minus 7x squared plus 11x, but this time we're integrating from 0 to the middle point, 2.38 dx. And this, again, you'll have to take the following on faith. Once we get to chapter 6, we're going to discuss in detail how to compute integrals like this. But for now, believe me when I note that this integral is equal to 7.72. Whereas a2, which is going to be this integral over here, so maybe more appropriately I should write that as negative a2, This is the integral of the same function x cubed minus 7x squared plus 11x, but now I'm integrating from 2.38 all the way up to a 4 dx. Predictably, when you compute this integral, we should be getting a negative value because this area lies below the x-axis, and indeed we get negative 5.05. So the conclusion is that the integral of this function x cubed minus 7x squared plus 11x from 0 to 4 dx is of course going to be the area of the first split minus the second split. Or I'm sorry, the area of the first split plus the area of the second split, but the second split is negative. So this is going to be equal to a1 plus negative a2, which is going to be 7.72 minus 5.05, which is 2.67. So here again, we're registering signed area because the positive, and we'll say that the area above the x-axis and the area beneath the x-axis are somehow canceling each other out. Whereas the other question one might ask is, with the same function, what is the total area? That's the operative word here. What is the total area of the region between the graph of f of x equals x cubed minus 7x squared plus 11x and the x-axis, specifically from 0 to 4 is what they're asking. And here we have to note that the total area, this means I'm not allowing anything below the x-axis to be a negative. So the total area is not going to have this negative in it. It's just going to be straight up a1 plus a2. So in this case, it's 7.72 coming from the first hump plus 5.05 coming from the second hump, which is 12.77. So the total area here, again, is the unsigned area. That's just the amount of material you'd need to fill the area between your function's graph and the x-axis. Whereas the integral is actually asking positive or negative and allows then for subsequent cancellation. So you have to be careful about the differences highlighted on the previous page between the notion of signed area and unsigned total area. Now, the last topic we're going to visit here is taking everything we're learning here and extending it just a little bit further. Notice here that I keep asking for the distance or the area between a curve and the x-axis. But the x-axis, we might write this as a little aside up here. Remember that the x-axis is actually a line. It's the line y equals 0. So we're actually, every time we've been talking about this integral, we're actually computing the area between an interesting curve and the completely non-interesting curve of this straight, flat, horizontal line. But with this perspective, we can actually extend our current conversation to allow us to compute areas not necessarily between a function and the axis, but between two functions. And that's what we have here, the area between two curves. If we draw a picture, essentially what we can do is the following. If this is our left endpoint A and our right endpoint B, we can have one function that looks like that. There's f. We could have another function, say g, so we'll call this function f of x and this function g of x, and we can then bound ourselves at A on the left and B on the right, And we could instead now start asking questions about what the area is between these two functions. So we might be bounded above by the f and below by the g, but this could be an interesting question we try to answer, is what is the area of that shaded region? It turns out that it's actually fairly easy to compute these areas. Effectively, what you end up doing is you end up looking at a similar integral as before, but the difference is that the heights of any sort of representative slice, like say that height right there, that distance of that line is literally equal to f of that value minus g of that value. So that's actually equal to something, if this is the point C on the axis, that's equal to f of c minus g of c. And so the only difference is, instead of, as you move from A to B, taking heights of just f, now you're just doing f of c minus f of g as it moves across this region. And so at the end of the day, this becomes our formula. We have that the area between the graphs f and g from A to B is just equal to the same integral, but now of f minus g. So for example, if we have these two graphs, notably, these are the functions f of x, which is 4x minus x squared, and g of x, which is 1/2 x to the 3/2. And in particular, we ask for only the parts of these graphs that live for positive x. That's the picture that we might have here. We want to write down a definite integral to estimate the area enclosed by the graphs. So that might be this area right here, where f is our upper bound and g is our lower bound. So that might be that area right there. We do have to make a special note. The left endpoint was that a equals 0. The right endpoint is going to be that magic value, which is going to be our b value. And oftentimes when you want to find the area between curves, you have to actually find that value. We'll save ourselves the time here, and I'll just note for all of you at home that f and g are the same, and therefore intersect at that point. If you set these two equations equal to each other and then use algebra to solve, you'll find that this will occur at 3.12. So if I want to find the area between these two curves, f and g, from 0 to 3.12, the formula says I find the integral of f minus g, where actually an important note should probably be made here. It's always the top function minus the bottom function, where you'll notice that this is the top function and this is the bottom function. It is important to note which one comes first. So in this case, again, we note here that the top function is f and the bottom function is g. And so therefore, if I give this area a name, maybe I call it a, I'll find that a is written as the integral from 0 to 3.12 of the top function f of x minus the bottom function g of x dx, which is going to be the integral from 0 to 3.12 of 4x minus x squared minus g of x, which is 1/2 x to the 3/2 dx. And again, at the current stage of the game, this is an okay answer. Once we learn more material in Chapter 6, we'll learn how to evaluate this integral, and you'll eventually be able to verify that this is equal to 5.906. I will say that for the purposes of the homework problems that you work on practicing this content, leaving your answer as a setup integral like that is going to be sufficient. So please keep that in mind. However, this example illustrates how we can extend the notion of the definite integral and how it relates to area under the curve and use it to help compute not just the area under a single curve, but now the area between two given curves. So this is going to finish our conversation on section 5.3. There is more than enough information here to help you tackle some of the homework problems and verify your mastery and understanding of the concepts underlying definite integration. Next lesson, we are going to jump into chapter 6, where we're going to learn how to evaluate integrals like the one we had at the end of this problem. Until then, however, work hard on the homework. Let me know if you have any questions, and I will catch you all in the next one.